Hello there, Mr. Chan here for Algebra 2, 5-1, nth roots, radicals, and rational exponents. Please grab your note takers and turn to page 113 and let's get started. We're going to explore powers and roots of these types of functions and including rationals as well. We have an opener here showing the graph of y equals x squared. As we know from Algebra 1 and some parts of Algebra 2, this is the parent graph of a parabola. Y equals x squared. The graph itself that they gave us in our note taker is not to scale, so be careful there. They do have, we can identify certain points like 0, 0, 1, 1, and 2, 4. It's also mirrored here on the other side of this parabola. We're going to go ahead and identify some of the values here. Okay, let's take a look at a little a. So they ask us, hey, what's the y value when x equals 2? If you go to 2 here, the value up there is definitely, let's take a look there, using the graph to explore, or you can actually plug it into the calculator. 2 squared is literally 4. That was easy. How about 3? When x is 3, what's y value? Well, 3 squared is 9. I mean, we can find that too on the graph. They're saying that that is 9 up there. Let's keep throwing some numbers in here. -3, that's still just like the last one. -3 squared, the whole thing is +9. Great. How about 5? 5 is actually kind of off the chart, isn't it? But when x is 5, all you have to do is just mentally put it into your head. 5 squared is 25. Okay, so the first row of problems here, they give you the domain value and go along the x-axis and just try to find that. Now the next row, they don't give us the x values, they give us the y values instead. Huh. What's the x value when y equals 4 or -16 or 7 or +5? So what you want to do is look along the y-axis and go to those values there and see what happens. Hey, what value will give you +4? What value of x will give you +4? Now, if we look at our first problem there, the answer's staring at us right there. That x value is 2. But what else will give us +4? -2. Both of them work, okay? +2 and -2, whoops, will give us a y value of 4, as you can see right here and right there, okay? How about -16? Do I have any y values that are -16 for letter F? The answer is no. There's none there physically on there. You can actually try to solve it. I mean, right now we have no real solutions actually. You can imagine when it comes to imaginaries, we could have an imaginary answer. So the answer could be, what's the square root of -16? Well, that's 4i. Something to kind of remind you of back in the day. Remember, the square root of -1 is I. That's your imaginary number, the imaginary unit. Okay, from last semester. How about 7? Well, you just do the opposite of square, you just square rooting, you can kind of get an answer. It's a square root of 7, right? Think about that. Your parent graph is x squared, you just are doing the square root, basically. And when you do the square root, you do produce a plus or minus. I mean, technically, or -7 as well, technically. How about 5? Square root of 5. Or -square root of 5, okay? All right, we're just utilizing the graph to answer those questions. Letter B, write a precise set of instructions that show how to find an approximate value of the square root of 13 using the graph. Now, square root of 13 is the y value, right? Now think about this. The square root of 13 is a number we're not familiar with, but we are familiar with other numbers that are perfect squares. I mean, numbers that are near 13 are perfect squares are what? 9 and 16. Those are perfect squares that we know of. Square root of 9 is 3. Square root of 16 is 4. So the number 13 is between 9 and 16. Therefore, the square root of 13 is between 3 or 4. Okay? So that's one way of kind of approximating it. So we can just say 3.5-ish. That's an approximation. It's a good guess. That's called interpolation. You're just doing your best guess there. All right, let's try letter C next. Draw a graph of y equals x to the third. Uh-oh. We're changing parent graphs here. We're going to x cubed. This is a new parent function. What does that look like? Now, I'm going to go ahead and actually graph that on here in the graph paper. This is called a cubic function. Okay? Y equals x cubed is a cubic function. We can start with a quick t-chart, pick some x values, and plug it in. Negative 2 to the third is negative 8. Think about it. Negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. Negative 1 cubed is negative 1. 0 cubed, of course, is 0. 1, 1, 2, 8. Okay? We're going to go by 2's on this graph paper because there's not enough room to represent all that. And it's going to plot those points. This is the cubic function, x to the third. So here we go. Negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, 2, 8. This is a curvy graph. It's really cool. Whoa. Whoops, I missed that one, didn't I? Try again. Very cool. That is y equals x cubed. Now, there are 6 questions here that they're asking us to do. And the order in which they are asking us to do this is kind of backwards, to be honest. I'm going to do D, E, F first, okay? I'm going to do D, E, F. They're saying, hey, a solution to x to the third equals 5. X equals third equals 5. Go on the y-axis and look at the value of 5. This is the y value, okay? Go to 5 here. Here's 5. And then from there, on the y-axis, scooch on over to the graph itself to the right, and there it is. It's almost hitting right there, isn't it? It's hard to tell, but that value is very hard to distinguish on the graph itself because it's not accurate. But on the calculator, and I'll show you that later, the value for x that will make your y value 5 is about 1.71-ish. Let's write that down. X equals 1.71-ish. Okay? It's approximate. In algebra, approximate are these like curvy equal signs there, okay? All right. So in fact, that actually answers letter A. D and A are actually linked together as questions. They're just asking it differently. Hey, what's the square root of 5? Cube root of 5, I'm sorry, that's how you say that one. Cube root of 5 is 1.71-ish. Okay? All right. Letter E. Hey, what is the solution to x to the third equals negative 5? Negative 5 is down here. That's kind of the same. I mean, notice some symmetry here about this cubic function. This cubic function actually has rotational symmetry. symmetry. That's one of the special characteristics of this particular function. It rotates 180 onto itself. In fact, letter E is basically kind of like the answer for letter D. In this case, it's negative 1.7-ish, okay? Right there. Let's write that down. Again, you're probably wondering what the heck's going on. We are using the graph of x to the third to find the answer to, hey, where does it equal to negative 5? It's about negative 1.71-ish. Okay? And that is actually the answer to letter B as well. There is such thing as the cube root of negative 5. You are allowed to do odd roots of negative numbers. Okay? All right, next one. A solution to x to the third equals 8. That one we actually have in our t-chart. Yay. There it is. The answer is 2. Okay, let's see. That's pretty easy. It's the same as letter C. So it's kind of a weird way of asking these questions. Yay. X equals 2. So we're inspecting a graph to answer these questions. All right. Now, let's take a look. And before we answer the habits of mind at the bottom, I need to do a quick review about rational exponents before we can move on to this lecture. So let's find some white space here and discuss this. Rational exponents are something that you learn in Algebra 1. And go ahead and walk it over with you. A rational exponent is also known as a fraction power. It kind of ties in with the x squared parabola and the x cube, the cubic function, because of powers and roots. Rational exponents combine both of them together into one operation. It's a fraction power. In algebra, a fraction power gives you both operators at once as a fraction. It's kind of weird. So here it is. A to the m over n represents the nth root of a to the m power. M is the power. It's the number on top. N is the root. You could have square roots, fourth roots, cube roots, fifth roots, etc., etc., okay? A to the m over n, again, is a fraction power form. You might hear it as rational exponent form, fraction power form, same thing. The other one, of course, should be look familiar. This, of course, is the nth root of a to the m. This is the radical form. If you have any questions about this, this is something from Algebra 1, let me know right away because it's going to seem a little bit challenging if you are unsure. Quick example. In order to save some time and room, if you get a problem like this, 5 to the 2/3 power, it doesn't mean that your answer is a fraction. It just means it has both a power and a root at the same time. This is equal to, if we convert it into radical form, the cube root of 5 squared. You can see it as also the cube root of 5 squared like that. They both mean the same thing. I mean, literally, you can see it as this. 5 times 5. I don't have enough to come out of the radical, but that's what I wanted to tell you about that one, okay? Also, when you look at the radical itself, the cube root of 5 squared, just want to remind you of what all the parts are. The 3 is also known as the index. We call it a root up there. They mean the same thing. The symbol of itself, of course, is called the radical. And the number inside has a name. This is called the radicand. And of course, we have the power over there. Okay, a lot of little parts. All right. So this will help us with answering the habits of mind question at the bottom here. How is the 6th root of 5 related to the cube root of 5? Now let's put on our thinking caps here, okay? The 6th root of 5 and the cube root of 5, well, the 5, the radicand, is equal, but how is the 6 related to the 3? So we got to think about this kind of in a strange way. Ready? Here we go. Think of the 6th root of 5 as, when we convert it to fraction form, 5 to the 1/6 power. Yeah? Now, hold on a second. What just happened? There's an invisible power of 1 right there in the original problem, and that goes on top. That's the power of 1. The 6 is the index. That's telling you how many you need to come out of the radical, okay? Now, how can we connect it to here, though? 6 can be broken up into 2 times 3. Isn't that weird? So would you agree that this is now 5 to the 1/3 times 2 power? Isn't that strange? I'm going to keep going here. It's going to seem kind of weird. 1/3 times 2, you guys agree if I go backwards with just basic arithmetic here, you guys agree it's 1/3 times 1/2? Yeah, this is really strange, isn't it? And if I keep going backwards, applying the power of a power rule, but backwards, we have 2 powers multiplying. This is 5 to the 1/3 to the 1/2 power. Isn't that strange? So that's how it's related, because this guy up here is literally 5 to the 1/3 power. So how is it related? It's basically this power relative to that. It's a 1/2 power. In fact, from Algebra 1, you might remember 1/2 power is the square root. Something you should have memorized. So the 6th root of 5 is the square root of the cube root of 5. Let's write that down as an answer. Wow, that hurt the brain, didn't it? The 6th root of 5 is the square root of the cube root of 5. And that's how they're related. Square root is that 1/2 power from a second ago. That hurt the brain. Next page. So we have an oldie and then we have a new one, paragraph. Quick little sidebar here. X squared we know is a parabola. Okay. X cubed we just shown you as an introduction is called a cubic function. And it looks like this. It's a little more exaggerated. We will be exploring roots. What are roots besides something plants and trees and grass have? Roots are where they cross the x-axis. And we're dealing with a coordinate plane that's the real Cartesian coordinate plane. So we'll just look at real roots. Roots are also known as x-intercepts, also known as solutions, also known as zeros. They all mean the same thing, where it crosses the x-axis. Okay? When you have a parabola or a cubic function, they'll eventually, or they won't, depending on which one, cross the x-axis. So I'm not going to do the one in the note taker yet. I want to do the one in the book. Okay? All right, this is actually from your textbook. Write this down on the left side. Here we go. What are the real cube roots of 125? They say the word real. This is basically where it crosses the x-axis. 125 is a number that looks kind of familiar. Is it related to 5? Now, how do you set this up? You have to come up with an equation. Here it is. X to the third, that's where the cube comes in, equals to 125. Using order of operations, we're going to go ahead and undo operations and solve this problem. There's actually 2 ways to do this problem, okay? If I move the 125 over by subtracting, my equation now becomes x to the third minus 125 equals 0. Whoa. And by the way, if you check with your graphing calculator or regular scientific calculator, you can actually solve this problem originally right here, applying the cube root function, because the opposite of cube is cube root. On the graphing calculator, if you cube root both sides, you'll get simply x equals 5. That's the answer. Is that all the answer? I don't know. So I'm going to do this problem 2 ways. So you can see that you have to keep in mind, we have to keep track of all the possible roots that are real. Okay, now here's the thing. X cubed, back to the green function here, the green letter here. X to the third minus 125 is actually a special polynomial that can be factored. You guys recognize it? We have a cube and 125 is 5? Oh, those are perfect cubes, ladies and gentlemen. This is a difference of perfect cubes. And there's a actual formula that we can use to factor it. Here it is off to the side. A cubed minus b cubed equals to a minus b times a squared plus ab plus b squared. This is a formula that we give you on the final. You don't have to memorize this, but you have to recognize it as being a difference of perfect cubes. And when we know that, looking at this problem here, the cube root of x cubed is x. We're going to use that formula. The cube root of 125 is 5. Okay? Recognizing that relationship there. I'm now going to use a equals x and b equals 5 and just write it down in that form right there, okay? And that'll give me my factor. All right, so a minus b, x minus 5, great. A squared plus a times b plus b squared. I'm just using the formula right there. So when I do that, I get this. Split up and solve. X minus 5 equals 0. X squared plus 5x plus 25 equals 0. The first one's easy. Oh, there's my answer again. X equals 5 from the graphing calculator. Great. The other one's a little bit trickier. The other one, you may recall, if you had to solve this, and if you can't factor 25 to get 5 with your AC method or guess and check, it's probably a decimal or a fraction, or it could be imaginary. You can do a quick check with your discriminant. The discriminant is b squared minus 4ac. That's a quick way of checking, as you call from Algebra 1, if you have any real or imaginary roots. All right? A equals 1, B equals 5, C equals 25. Let's plug the numbers in. B squared. B is 5, squared minus 4, A is 1, C is 25. So we have 25 minus 4 times 1 times 25 is 100. Aha! 25 minus 100 is negative 75. The discriminant is negative. Remember, the discriminant is part of the quadratic formula. If you try to take the square root of a negative number, it's impossible. This is a negative number. A negative number underneath the radical is not allowed. This is imaginary. So this means that these are imaginary roots. In fact, there are two of them. We have one real root and one imaginary root. 1 plus 2 is 3. That's something that we notice, is that the number of roots do add up to the power of the original problem. Now, think about this particular graph, okay? So I want to tell you. X to the third, or some form of it, actually, what we drew up here earlier, can cross the x-axis. Like this possibility. It can cross once. It can cross 3 times. Let me show you. Watch this. Depending on how curvy it is. I've just drawn for you the 2 possible ways of graphing x cubed, depending on the actual numbers it's involved. Those are the 2 possibilities. 1 real or 3 real roots. Okay? All right. So keep that in mind. Cube could have those 2 possibilities. You guys ready for the note takers example? Let's go ahead and do that. All right. Number 1. Same process as what we did on the left side there. Hey, let's find the 4 roots of 81. Again, you can do this 2 ways. We can do the graphing calculator, but if we do the graphing calculator, we're kind of missing all the other possible roots that are out there. So I'm actually going to do this algebraically. We're doing real 4th roots here. Here we go. X to the 4th equals 81. Let's go ahead and move the 81 to the other side. X to the 4th minus 81 equals 0. Interesting. Isn't that a difference of squares? Yeah, x to the 4th is a difference of squares. That's something that you should recognize from Algebra 1. Aha, let's factor that. The square root of x to the 4th is x squared. Kind of interesting. The square root of 81 is 9. Minus plus equals 0. Interesting. These 2 factors here, one of them can go further. There's another difference of squares. The first one, x squared minus 9. But the second one cannot go further without becoming imaginary roots. X squared plus 9, if you try to solve that, you'll get imaginary roots there, okay? Because there's no number that will give you negative to 0 out the 9, okay? That's impossible. So x squared minus 9 is also a difference of squares, just like the last one above it. So x squared minus 9, that can be broken down further. That becomes x minus 3, x plus 3. Yay, those all equal to 0. Split them up and solve. X minus 3 equals 0, x plus 3 equals 0. I mean, I'll even show you. X squared plus 9 equals 0. If we try to solve all this stuff, I just want to show you. All right. X equals 3, x equals negative 3, x squared equals negative 9. You see where the problem is if you try to square root both sides? Ooh, those are imaginary roots. We don't need those. We only need the real roots. And they are dun, da, 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 x equals 3 or negative 3, okay? Technically, those imaginary roots are plus or minus 3i. That you might recall from before. Woo! So far, we've come across some interesting challenges when it comes to powers and factoring and solving. Let's try letter B here. Here we go. Let's find real cube roots. Let's do that. Next. X to the third equals 64. Subtract 64 to both sides. This is a difference of cubes. Yay. We have the formula from earlier that we're going to utilize. Ooh, the cube root of x to the third is x. Nice. So we're going to use that, okay, in that formula. A equals x. The cube root of 64 is 4. So let's use that formula, okay? A minus b times a squared plus ab plus b squared. Let me put those numbers in. So we have our x and our 4. And clean that up. And you guessed it. Usually the back half of this factored polynomial is usually imaginary. We'll prove that really quick as well. X minus 4 equals 0, x equals 4. That's one of my real roots. Is that the same for the other one? Do a quick check with the discriminant. B squared minus 4ac. A is 1, B is 4, C is 16. Plug those numbers in. 4 squared minus 4 times 1 times 16. Yep, that's going to be negative right there. In fact, that's negative 48. Dun, 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 dun. Is imaginary roots. Because your discriminant's negative and you can't take the square root of a negative number as part of the quadratic formula that we've done before in Algebra 1. All right. Any questions about example 1? That's kind of hefty. Let's go to example 2. Explain what each fractional exponent means, then evaluate. Okay, this is where we continue on with Algebra 1. We're actually going to do these problems. They are in fraction power form, 25 to the 1/2 power. Don't forget, just want to remind you that a to the m over n from Algebra 1 is equal to nth root of a to the m. Sometimes when you can't see it in front of you or punch it in a calculator, you might want to convert it to the other form. Right now it's in rational exponent form or fraction power. Let's convert it to radical form. Okay, I always like to do this first. 25 is the base, the power is 1, and the index is 2. Oh, that's the square root of 25. What is the square root of 25, class? 5. That's it. Pretty easy. Not too bad. Can you guys memorize that for me, folks? 1/2 power means square root. Just something easy to just memorize from now on. Yay, not too bad. Any questions there? So it's easy sometimes to manually convert it to radical form and then see how things come out of that radical, okay? All right, how about the next one? 32 to the 2/5 power. It's, of course, in rational exponent form or fraction power form. Let's convert it to radical form. Here we go. Radical, base is 32. The power on top is a 2. And the number on the bottom is the root, of course. It goes right there. Oh, we're doing the 5th root. Okay. Keep in mind, that means we need 5 factors, okay? Now, right now, you don't see it, but if I take that 32 and break it down, I'll get this. Yeah, we got to simplify these radicals, but with different indexes or roots, okay? This is your index or root. We need 5 of them. That's the key here. Whoops, one color. Break that down. Now 32 is 2, 2, 2, 2, 2, but there's double of those number of 2's because it's squared. So the 5th root of 32 squared is literally this problem. How many are we looking for? We're looking for 5 of them. Oh, look, that all 5 of those comes out as a single 2 on the outside. And this second group of 2's come out as a single 2 as well. Bam. And there's nothing left underneath the radical, so that goes away because there's nothing else left there. So the 2 and the 2 that come out is literally 2 times 2, or simply 4. That's your answer. 32, you can try this on your calculator. You can just punch it in if you want to try it. 32 to the power of 2/5 will give you this answer of 4, okay? All right. Any questions? Woo! Habits of mind. What is true about the denominators of fractional exponents in which absolute values must be considered? You have to look at the index power, okay? Look at the index. Is the index odd or is it even? That's the key to today's lesson so far. We've been playing around with evens and odd roots. What if we had 100 to the 1/3 power? Its root is odd. Versus, how about another one? 75 to the 1/2 power, let's say. The root there is even. Okay? Here's the thing. You cannot take the even power of a negative number. The even root of a negative number is not allowed. You can take an odd root of negative numbers, but not an even number. That's what they want us to understand. That leads us to example 3. Ready? Woo! All right, here we go. What is the value of each expression? Round to the nearest hundredth if necessary. All right. Some things to think about in this first problem. We have a negative to worry about. Holy cow. That's not even part of the problem. That negative will be attached to the answer at the end. Okay? But we do have 16 to the 3/4 power. So I would like to look at it this way. Negative 16 as a radical like this. 16 to the 3rd, and we have a 4 index. I like to expand those powers a lot of times. Negative 4th root of 16 times 16 times 16. A lot of different ways to expand that, right? 16 itself can be broken down too into a bunch of 2's. In fact, if you think about it, 16 is 2 times 2 times 2 times 2, basically 4 of them. Okay? In fact, there's a bunch more right there. What are we looking for? We're trying to take the root, the 4th root of 16, 16, 16. We need 4 of them. That's my index or root. Oh, psh, there's a first grouping of 2's, and psh, take out another quadruple of 2's, and finally, psh, a third quadruple of 2's. There's no more left underneath. And who's waiting on the outside? You remember that? We had a negative sign. So there it is, ladies and gentlemen. Negative 2 times 2 times 2 is negative 8. That's your final answer. Okay? All right. That's using radicals. Did you know that this problem could have been done in a different way? I'm going to show you. I know this is turning out to be a long lecture, but I just want to show you there's an alternative. Or stick with the fraction power, but look at 16 as a different way. Think of 16 as 2, 2, 2, 2, or simply 2 to the 4th power. Okay? So I'm going to rewrite the problem as negative 2 to the 4th power, that's 16, to the 3/4 power from earlier. This is 16 now, okay? Oh, this is interesting. We have 2 to the 4th to the 3/4. Power, the rule is to multiply. 2 to the 4 multiply with the other power 3/4. Ooh, you guys know how to multiply fractions, right? Hey, look at those 4's. They cancel. See that? What are you left with? 2 to the 3rd. What? What is this? What is 2 to the 3rd? Oh, it's just 2 times 2 times 2. Or negative 8. There's your answer, just using fraction powers, okay? All right. The next one's kind of boring. It is a decimal. We don't have any tools besides a calculator, so I would just definitely ask you guys to plug it in, no big deal. You can literally do this as, remember, this is the power right here, the 4 is the power, and the 5 is the index, right? Okay, so this is just basically on the calculator. 3.5 to the power of, and use parentheses. Don't use the ABC button. I don't trust it that much, depending on which manufacturer's ABC button. I would use parentheses and a division symbol. 4 divided by 5. And when you punch that all in, it will approximately give you 2.72 when you round to the nearest hundredth. Okay? So that's using fraction powers. You can actually, on some calculators, just punch it in how it looks. You can punch it in this way as well. The 5th root of, so I will, let me do that again. Punch in the number 5 to start out the index and find this button on your calculator, the X root button. And 3.5 to the power of 4. And you'll get the same answer too, okay? You should. All right. Let's go to the next page. If you have any questions, let me know. So far, examples 1, 2, and 3 involve numbers. What happens when we start dealing with variables? Okay. Now, just a little carryover. There is a difference when it comes to cube roots and square roots and 4th roots and 5th roots. You look at whether the index or the root number is even or odd. So I just want to point that out right now for you. When they're odd, like number 4a, you don't have to really worry much about it. But later on, when they're an even root, you got to worry about that. And the thing you have to worry about with even roots is, what if the variable, because we're doing variables now, what if the variable is negative? How do you take care of that? And that's a question that will pop up on SATs and ACTs. What if the variables are negative? Write that down. So even roots are important for negative variables, and we have to point that out. Odd roots is no big deal. We can take the odd root of negative numbers, and that's allowed with the cubic function, okay? All right. So 4a, we're looking for the cube root, meaning we need 3 of something to come out as a single copy of itself. What you can do is break down negative 8, a to the 3rd, b to the 9th individually. I just want to show you manually what that looks like, okay? Let's write this down. With the cube root of all those numbers. Now, -8 can be broken down as -2 times -2 times -2. That's allowed. Or you can just say -1 times 8 and break up -1 individually, doesn't matter. A to the third, B to the 9th. I know this is kind of silly. I'm doing it the long way for us to kind of show you what the process is. Manually, we're trying to bring out a cube root, okay? We're trying to do that right now. So, forgive the telephone, sorry about that. All right. Hey, yo, do we have triples of everything? That's what we're looking for. We're looking for triples right now. Oh yeah, we do. Here's a triple. Triple 2, -2. That comes out. Oh, we have a triple A. That comes out as a single A. Hey, we also have another triple B, another triple B, and a third triple B. And nothing is left underneath. Ladies and gentlemen, that is your answer right there. -2 times A times B, B, B. And that simplifies to -2AB to the third power. Yay. That's one way of looking at it. And there's another way. There's actually another way to do this problem. I have to show you this, and I apologize. Here we go. Instead of using the radical, let's convert it to a fraction power. You have to treat that cube root as 1/3. Cube root, see that 3 right there, is the 1/3 power. Okay? I know this is going to look weird. The radicand, -8, A to the third, B to the 9th, to all of it to the 1/3 power. 1 is that power, it's just a 1, it's just an invisible 1. That 3 is the index, of course, right? That is the root. Now, back in Algebra 1, when it comes to powers, you apply the power to everything. So I'm going to apply everything inside the parentheses to the 1/3 power. -8 to the 1/3. Right? A to the third to the 1/3. This is crazy, huh? This is just another way of doing this. B to the 9th to the 1/3. Wow, that's crazy, okay? Now, -8 to the 1/3 power is literally the cube root of -8 by itself, which we know is -2. A to the third to the 1/3 power, you multiply those powers. Oh, look at that. 3 and 3 cancel out. That gives you A to the first. How about the other one? B to the 9 to the 1/3 power? You multiply those. And you see the reduction there as a fraction? Yeah, isn't that weird? And there you go, ladies and gentlemen. The answer done a different way. Mind blown? All right. This leads me to even roots. The number 4 is an even root. This is where we have to take special care. And I just want to tell you ahead of time, I'm actually going to skip this part right here and focus on 4B right now. Okay? Let me know if you guys have any questions. It's kind of crazy. We're going to break down the 256 x to the 12th, y to the 24th. Okay? We don't know if the variables that we get as an answer is negative or not. There's an easy way to make sure that they become positive. Okay? We can't take the square root of negative numbers. That's going on here. Okay? 256 is actually a number that is breakdownable. And trust me on this. 256 is actually a perfect fourth power of 4. Crazy. I'm not going to break down the fours further because I only need 4 of them, and there they are. 4 to the 4th power is 256. Crazy. X to the 12th is breakdownable. I'm going to do it as x to the 3rd, x to the 3rd, x to the 3rd, x to the 3rd. Now think about that for a second. 3 plus 3 plus 3 plus 3 is 12. I'm breaking it down into 4 groupings to make life easier. Y to the 24th is the same thing. You can divide 24 by 4 as well. You're going to have 6 of those. Isn't that crazy? Okay. Just writing it all down. You're basically dividing them up. All right. What are we looking for? We're looking for 4 of each thing, okay? So we got the first 4 of 4s, that comes out. Nice. The x's, holy cow. There's a group of 4 of them, that comes out too, x to the 3rd, okay? How about the y to the 6s? Did I put them right to the 4s? That's kind of weird. I meant to put 6, didn't I? Yeah, sorry about that. I'm glad I caught myself. That should be y to the 6. Whoops. How silly of me. That comes out as a grouping as well, as y to the 6. Now here's the thing with our answer. Look at the variable x and the variable y. If x was negative, negative whatever the number is to the 3rd power will still be negative. I can't have an answer that comes out negative. So I have to make it positive. I have to force it to be positive. Boom. I'm going to use an absolute value function because what if x is negative? That's a problem. So to force it to be positive, I'm going to use absolute value there. That's a weird thing, isn't it? The absolute value makes it positive. What if y was negative? Well, it doesn't matter. How many y's do you have? You have 6 of them. If you have an even number of y's that are negative, it will become positive by itself. So it's done. So ladies and gentlemen, this is the answer traditionally. Okay? If you don't use absolute value, sometimes they'll let you get away with plus or minus 4 x to the 3rd y to the 6. That's telling the reader that you don't know if it's going to be positive or negative. So both of these are actually answers to even root problems. Woo, crazy. All right, let's move on to number 5 here. Here we go. This is definitely a very extensive lesson today. All right, let's go and solve these problems here. We're actually solving for x. You've learned a lot. When it comes to solving, we're still doing PEMDAS backwards. Don't forget that. We're undoing operations. Okay, here we go. Let's isolate x in the first problem. Let's divide by 3 to both sides, 5 to both sides there. Pretending this is an actual real problem there. We now have x to the 3rd equals 5. Does go into 320 64 times. Hey, wait a second. That looks familiar. Let's think about the inverse operation that would get rid of that cube. The opposite of cube is cube root both sides. This is an odd root. We don't have to worry about pluses or minuses, do we? So the opposite of cube is cube root both sides. Okay, there's no plus or minus here. Trust me. The cube root of 64 is 4. Ding, 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 ding. Not too bad. All right. Let's try number 5b next. Let's go ahead and divide by 2 to both sides. P to the 4th equals 81. Aha. Technically, you can move the 81 over and try to factor it, blah, blah, blah. You'll get the same answer if you just go ahead and do the opposite of 4th power. Because right now we're doing nth roots. This is the technique for these 2 problems. There's actually 2 ways of doing these problems, by the way. And you know, I'm not actually going to do it. I'm just going to say or. X cubed minus 64 equals blah, blah, blah. We're not going to do that. Here's the same thing. Same thing. You can do this if you wanted to. p to the fourth minus 81 equals 0. But we're not doing that. We're doing it the nth root way to solve. Okay, we're doing the opposite operation. All right, just want to make that clear. All right, we have an even root right now with the second one. Ouch. Whenever you have even roots, you do need to produce or introduce a plus or minus. That's important. Okay, so let's go and do the fourth root of both sides. It's kind of weird doing a fourth root, isn't it? Let me know if you have any questions. This is kind of crazy stuff. The fourth root of 81 is, da, 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 da. If you try it on a calculator, break it down by hand. It is 3, ladies and gentlemen. There it is. P equals now not just positive 3, but also negative 3. Okay, they both work in that equation. Because negative 3 to the fourth power is positive in that original problem if you were to check it. Woo! All right. How are we doing out there? Okay. I'm actually going to skip number 6. I actually did it last year. You can check the notes online at my website. I'm going to skip it for this video. It's turning out to be a really lengthy video. Let's jump to the last page, okay? Let's just get to the last page. We're approaching 1 hour here. Holy cow. So here I'm going to write down C online notes. It's a word problem. I understand. It's going to take a lot longer than I expected. All right, last page. Thanks for hanging in there. Let's convert it to radical form. Just a quick reminder. We're doing number 7 right now. A to the m over n power is equal to the nth root of a to the m. We're just converting. That's all we're doing with number 7. Yay, let's put in a radical form. A. Oh, we're doing 1/5 power. This is 1/5. Done. That was easy. Woohoo! That's number 7. Okay, number 8, same way. Let's convert that. Radicals. We're going to radical form now. The base is 7, the power on top is 2, and the index is 3. Bam, there it is. We're not solving it. We're just trying to convert it to the other form. No big deal. And thank goodness, number 9 is going the other way. We're going to radical form. Exponential form. Sorry. We're going the other way. So b is the base to the power 1/3. Notice I wrote the 1 there to show it's invisible. Great. Number 10. The base is 3, power 7 right there over 4 power. Yay. That wasn't that bad. Woo! Wow. All right. Let me zoom in a little more so you can have a little more room and see everything. Number 11. How many real third roots does 1728 have? Let's solve that. We do need to set up an equation. X to the third equals 1728. You can actually do this 2 ways. We're going to do the traditional way, subtract 1728 to the other side. I wish they didn't give us such a huge, scary number. 1728, ladies and gentlemen, is cube rootable. It's crazy. The cube root of 1728 is 12. We do recognize this as being a difference of cubes. And we need to use our formula that we had from earlier. And I'll just write it off to the side because I have a feeling we're going to have to be using it again or something like that. It is a cube minus b cubed equals 2a minus b times a squared plus ab plus b squared. We've got to use that formula, folks. Sorry. And in this case here, a equals x, because that's the cube root of x cubed. And b equals 12. Yeah, 12 times 12 times 12 is 1728. Pretty crazy. So let's go and form this. And we'll get, all right, here we go. X minus 12, x squared plus 12x plus 12 squared, which is 144. Can you tell that my discriminant is definitely going to be imaginary? This is imaginary right here. Trust me. Because of b squared minus 4ac. There's only one real root, which is right there. X equals 12. You have one real root. That real root is 12. I wish they gave us more room for this. Sorry. That's all they gave us. If you graph this equation in a graphing calculator, x cubed minus 1728, it will cross the x-axis at positive 12. Okay? Number 12, speaking of, how many real 6 roots? Holy cow. We just did third roots. We're now doing 6 roots. Let's do that equation. Woo. This is turning out to be pretty crazy. This one especially. Let's move the 15,625 to the other side. By subtracting. This is actually another difference of cubes. You may not see it. It's hard to see. The cube root of x to the 6 is x squared. The cube root of 15,625 is, crazy enough, 25. Excuse me. Okay, using that formula, let's do it. This gives me some big numbers. I don't think you'll expect to see something like this on a test or a final, but this is pretty nuts. X squared minus 25 times x squared squared is x to the 4th eventually. I need a little more room there. Plus 25x squared. Woo! Plus 25 squared. Okay? Pretty nuts. Oh, wait, look at this. X squared minus 25 is another difference of squares. Holy cow, that breaks down. Unbelievable, Mr. Chan. This is the most lengthy lecture in our Algebra 2 career. The other one's imaginary. Trust me. But the one that we are interested in are these two. Here we have 2 real roots. They are 5 and negative 5. You can actually graph those. Kind of speeding up a little bit. Woo, crazy. All right. Number 13, let's solve this. Let's divide by 4 to both sides. You guys ready to protest? 4 goes into 3, 24, 81 times. Oh, interesting. 81, when you cube root it, is break it downable. Interesting, interesting. 81 is not a perfect cube. Excuse me. 81 is 9 times 9. 9 and 9 are 3, 3, 3, 3. I have extra here. Because it's an odd root, I don't need any pluses or minuses, do I? So I don't have to worry about that. Cool. But I have at least 3 3s. I don't need the 4th one, right? So those 3 come out as a single 3. And left over underneath, I have the cube root of that last 3 that I don't need anymore. Ladies and gentlemen, x is equal to 3 times the cube root of 3. That 3 that came out are the first 3 3s, but the last 3 is stuck underneath the radical, the cube root of 3. Isn't that weird? That's what the answer is. X equals to 3 cube root of 3 is the answer. Ooh. All right. Kind of picking up the speed here a little bit. Try to get this under an hour and 15 minutes. I can do it. Let's divide by 2 next on number 14. By now, I'm expecting you guys to go on strike. I wouldn't doubt it. 1250. Uh-oh, we have an even root. If I 4th root both sides, I need a plus or minus with that 4th root. 1250 is break-it-downable. Let's do it. I need 4 of anything. Ooh, interesting. 125 from earlier, we know it's 555, and 10 is 5 times 2. Look at that. 55552 is 1,250. Whew, yay. I have 4 something that comes out, but that 2 is a leftover. That's what's left underneath the radical. Dum, 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 dum. So this is plus or minus 5 times the, this is going to sound weird, 4th root of 2 is the answer. Okay? That is your x. Crazy. You guys ready for the last 2? These will go fast. I'm actually going to convert them to a fraction power form to show you how fast they can go. So right now it's in radical form. And I'm going to convert it to, of course, fraction power form. And the root here is the cube. That's a 1/3 power. Over here is 1/5. Yay! I don't have to worry about any even roots or any negative variables, so this is going to be easy. Let's do the first one here. This is 27x to the 12th y to the 6th to the 1/3 power. Let's apply the 1/3 power to every term inside the radical, which is the radicand. Let's do that. 12 to the 1/3, x to the 12th to the 1/3, y to the 6th to the 1/3 power. Power rule. By the way, the cube root of 27, oh, why did I put a 12 there? That was weird. Forgive me. That should be 27. Awkward. 27 is breakdownable. 3 times 9 and 3 times 3, right? So it is doable. The cube root of 27 is 3. So that gives me 3 times, okay, look at over here, power. 12 times 1/3 is x to the 4th, right? 3 goes into 12 4 times. Yay. And over here, oh, 3 goes into 6 twice, so that's y squared. Yeah, I got 7 minutes left. Can't believe I can do this. There's your answer for number 15. I don't have to worry about any negative because it's an odd root. They're both odd roots, so I don't have to worry about that. But earlier, when we did an even root, we had to do the vertical absolute value bars to make it positive, right? Or plus or minus. Last one here. Let's convert everything to 1/5 power. Excuse me. 1/5. 1/5. 1/5. Notice they're giving us numbers that would nicely break down. -32. That's kind of interesting. Is -2, -2, -2, -2, -2. Just from experience. There's actually 5 of them. They come out as a single -2. 5 to the x to the 5th to the 1/5. Reduce those. That's interesting. That's just x to the 1st. Huh. Cool. And over here, 5 goes into 36 times for that last one. Y to the 6. Wow, I don't know about you. I haven't done one of these in a long time. There's my answer. Thank you for hanging in there. Please don't hate me. Have a good day. Take it easy. Peace.